Good afternoon, ladies and gentlemen. Welcome back to another live stream. So we are back again with our movie ratings model. So last week we had started to train up the models that we were going to use for binary classification, and this week we are back with the regression models. So in case this is your first time tuning into one of these streams, especially with this particular project, let me just give a quick recap on the project. Trying to do this really quick because I want to delve into actual code. So what this project is doing is I listened to a kind of silly podcast where it's about a couple guys to just talk about whatever, and one of the segments of that one of the guys talks about is where he rates movies, and he rates the movies kind of with two different like review kind of scores. So one is by the way, I'm looking at myself in the mirror, so I barely made it to this live stream because I was outside playing in the snow with my girls and just barely had enough time to get in and shower and shave, and it looks like I might have accidentally scraped myself a little bit. Okay, anyway, what this effort is doing is we are so the reviewer of these movies gives two scores. He gives like basically a thumbs up or a thumbs down, a binary yes or no, and then he gives a second rating, which is like a traditional 0 to 10 rating, and it can be a single floating point decimal, so 3.3 or a 5.6, anything like that. So last week we got through testing pretty much all of the binary classification models for the actual yes or no. And this week we are going to pivot now over onto training some regression models that will help predict that 0 to 10 score. So we didn't get quite through everything last week. We made, I think that stream went like almost 2 hours, and I can't believe it went that fast. Actually, let me do a quick audio check here. I want to make sure that my audio is doing okay, doing just fine. All right, let me go ahead and share my screen here. And so there were actually two things. Let me scroll back up to the top here. Two things I did kind of stupidly, like I was not thinking at all, and I've since corrected for them. So the first one was whenever so we have basically two predictor values here. So originally I had even said this in a live stream. I said, you know what, I think it'd be interesting to actually use the other predictor value as input to our data. And then I was sitting there realizing a couple days later, wait, I'm not gonna have that whenever we're actually doing inference. So like whenever we want to do inference on like trying to predict whatever this reviewer's next movie score is going to be, like that's not going to work because we're not going to have this score. So simple thing, I just dropped that column. So with the binary classification, like I said, it's a yes or no, so that's why it's Bean yes or no here. By the way, the reviewer's name is Kalen Bean, son of famous actor Michael Bean of like the Terminator movies. Okay, so there was that. So that was one little dumb thing I did. I guess I didn't do. Did I do anything else that was necessarily dumb? No. Now we didn't get through it because the furthest we got was we did the logistic regression model. We did the Gaussian naive Bayes. I feel like I'm talking really fast, but that's because we went so long last time, and my daughters want what they're calling a girls' night, except with dad. So it's still girls' night, but with dad. And so I'm looking forward to that. And so I don't want the stream to go too terribly long today. But anyway, so we got through the logistic regression model. We got through Gaussian naive Bayes. Then we had to do the support vector machine, specifically the support vector classifier. And so I was doing some research online with these different algorithms because some of these algorithms fare better if you perform a scaling on them, a scaling on the features. And so you might recall, like the furthest that we got in the stream last time is that we got to this point and then we were running into some errors. And the reason is because, and let me scroll back up here. So we'd created this master function that we're kind of reusing over and over with all these things. And so you can see if scaling is done on the data, we do it like this. We import a standard scalar from scikit-learn. So what the standard scalar is going to do is going to scale all of our values between -1 and 1 based off of a standard deviation value. And so that's what that does. And then we do a fit transform. But what I forgot is that like the output of this fit transform here is just a NumPy array. And given that the rest of this whole thing is using pandas data frames, I needed to refactor that to be a pandas data frame instead. So that you can see that's what we're doing on these lines right here. Just super simple. We're just taking the scaled features. We're setting the index to be the original X value here. and then the column to be the original X columns, and then it works just fine. So with that, I went ahead and did a little more alterations here to actually, I printed out the best hyperparameters for each. And then, so let's just go ahead and quickly review the binary classification models. So here's the interesting thing. So I purposely started with the logistic regression because logistic regression is probably the most simple binary classification algorithm you can use. It's nothing fancy under the hood, and so this is a great case. Well, before I talk about that, let me show the rest of the score. So here we get and all these you'll find actually have a terrible ROC AUC score. So here we have an accuracy score of 89%, an AUC ROC score of 54%, and then an F1 score of 88%. And then you can see down here, Gaussian naive Bayes fared about the same, more or less. Again, accuracy score being a 78%, ROC score being 50%, F1 again being 88%. So the support vector machine here actually fared a little bit worse in some aspects, so fared a little bit better in others. So fared a little, about the same with accuracy, a little bit better with the ROC AUC, but a little bit worse with F1 score. And then we jump down here again to the random forest classifier. So these last two model algorithms we did not get to, and that was the random forest classifier and the cat boost classifier. And so the random forest classifier, 77%, 49% for ROC score, and then 87% for the F1 score. I got to take a quick sip. I'm getting thirsty. Hope you all are staying safe out there. We in Illinois got a lot of snow. And I went out driving earlier, and fortunately I was fine, but the car in front of me, actually it was a two-car pileup. One guy was going way too fast, hit the guy in front of him, which caused that guy to hit the guy in front of him. So pretty unfortunate. Just be safe out there if you're here in Bloomington with me. Okay, so, and then the cat boost classifier, 78%, 50, and then 88. So all of these you can see all fare about more or less the same. And so, I'll go ahead and rerun all these because I actually built all these. So right now I'm operating on my Mac Mini computer. You can kind of see off the side over here. So if you follow me on LinkedIn or anything, you might know that I like to do, or did like to do, all my coding on an iPad, and I've recently pivoted over to using a Microsoft Surface instead. And so I actually did the remainder of this work on the Microsoft Surface, and I'm randomizing the splits and stuff every single time. So I'm very curious to see how this stuff will run when I run it all again. So let me go ahead and just restart this and clear out every single output of this notebook. All right, so restarted, and then let's go ahead and run these first couple cells. And fortunately, the Mac Mini here, because we are doing a grid search to make sure that we find the ideal hyperparameters, you'll see that the Mac Mini just chugs through these things very quickly. And this is one of the newer Mac Minis that, did I skip past one? Yeah, I did. I skipped past, oh my gosh, this is why, and I haven't even put cat boost on here. This is why I need to be better prepared. So sorry, like I said, I'm sliding into the stream hot from the snow, ironically, because it's not hot out there. All right, so let me quickly install cat boost here. Pip install cat boost. And so this is a kind of a bad practice because you should be using virtual machine. Could not find a version. What is it? What is going on here? Uh-oh. Let me find out. Did I run the wrong command? PyPy.org. So this is where I check to see easily, what's the name of one of these libraries. I thought it was just called cat boost. Yeah. So what's going on here? Pip install cat boost. Did I not write that correctly? Pip install cat boost. Okay. How about a pip 3 install cat boost? Install cat boost. Oh my gosh, from versions none. Well, what if I set the version very specifically? All right, this is weird. Because I just installed this on my Surface the other day and had no issues, so I might have to we might just have to skip over cat boost today. I hope not, because cat boost equals. All right, this is very odd. Could not. All right, well, what's going on with my pip? Pip version, pip 3, pip install, upgrade, pip. All right. I'm just trying out a couple different things. Maybe I just need to this is very odd. Okay, so I just updated my pip install cat boost. All right, are we gonna still have an issue here? Okay, well, something's wrong with cat boost. We're gonna just have to comment out this code for now. Apologize for that, but I'm gonna come back to here. Let me go ahead and comment this guy out for now. and then we'll just make sure to skip over those cells from previously. Okay, so ran that, and then let's go ahead and run all these cells except for the cat boost, apparently, because the cat boost does not want to install. That's super weird. Okay, I'll have to figure out that later. I'm not going to try worrying about that for now, although that does mean we're not going to be able to get to our 5th regression model, and that's okay. All right, so I am rerunning all these cells. You can see that we've already, my Mac Mini with the M1 chip here has already chugged through some of these. So we're getting similar scores here. So 79, 54, 88, 78, 50, 88. So far, logistic regression is doing the best. 78, 57, 87. So support vector machine, I actually have found that it's actually been performing just a hair better than the other algorithms. Now I did notice that the random forest classifier does take a little bit longer to train. Okay, but that one was still pretty quick. Oh, that one actually has now fared the best. 7962. Let's go ahead and rerun this because, like I said, these are we're doing a random k-folds validation here, and then I'm just taking the average of all the k-folds here to see what our score is. So I'm going to go ahead and rerun this and see if we get something similar. But you know, but my point was with all these things, all these algorithms is, you know, I'm gonna be totally honest. Like, I'm not super like into the math of these algorithms. I personally am just not. Like, I understand like what it's doing, like, but don't ask me to like write it down on paper or whatever. All right, so 76, 54, 86. So there, if they're a little worse. But my point is like, even if you are a mathematician and you think you know what the best answer is for any of like your problems, no, you don't. You don't, because like, basically what we're seeing here is that all of these algorithms are, and even, you know, we can't test out the cat boost classifier right now because I'm having that weird issue, but even the cat boost classifier, like, they all fared about the same. And so and that's considering, you know, logistic regression is a much simpler model, whereas random forest classifier and both cat boost classifier are what we call ensemble models, meaning that they are using an ensemble of sorts of different algorithms that are supposed to produce a better result. But as we're seeing, not really. So I do want to get the cat boost classifier working in. I haven't settled on which one I'm actually going to use as my final candidate. I'm leaning toward random forest classifier just because it's easiest to work with, and it seems to be faring just a hair better. Cat boost classifier was also doing pretty well, but cat boost is a little bit weird in the sense that, like, well, I can't show it on this machine, but like, if you're not careful about how you program these things, then it just starts just dumping a bunch of like logs at you. And so that's why I actually had to Google, like, how do I turn off of these logs? And so we have the silent equals true. And then the other thing is that it also dumps a bunch of information in a new directory that it just creates. And I don't know why, and I don't really want that. So, like, you know, at the end of the day, I think I might just end up going with the random forest classifier. But we're already 15 minutes in, and we are still not to the regression algorithms. So, and I'm, and again, I was hoping to be a little bit more prepared, because I was a little more prepared this last time because I actually had all this information about the algorithms up here. As you can see, I have selected the algorithms that we are going to be testing with down here in this block right here. Let me scroll up a little bit. So what we're going to be covering is we're going to do 4 scikit-learns and then 1 cat boost again, except we're not going to be able to do cat boost today, obviously. So we're going to do linear regression. We're going to do lasso regression. We're going to do the support vector regressor and the random forest regression models. And then, of course, we would do the the 5th one, cat boost, if we could. Okay, talking really fast. All right, so what we are going to do is, you know, so above here with the binary classification models, we had created a function that helped us to churn through all of these things very quickly. And for the most part, we can reuse this. So I actually just copied and pasted this whole thing down, but there are things that we need to alter to it. So scaling is fine. Grid search is fine. Doing a fit is fine. Finding the best parameter is fine. Now, what we need to change here is, first things first is we need to change the validation metrics. So the validation metrics are going to be different for our regression models here. So instead of accuracy, ROCOC, and F1, we are going to have mean absolute error, mean squared error, and R2, or an R2 score. So what we need to do is we need to alter these containers. So MAE scores, I already forget the other two. I have them up here though. Mean absolute error, mean squared error. And I don't know how you calculate, because I know that I think you can calculate a root mean squared error. I think I want to do the root mean squared error, or maybe both. Do I want to do both? Well, let me see how you even calculate this. So transparently, most of the models that I work with on a day-to-day basis are binary classifiers. So I don't do a whole lot with regression models, but I want to get into it a little bit more. All right, so let me just do a quick Google search here. Scikit-learn, and then mean squared error. Mean squared error. And I think the same function you can do a root mean squared error is, and you probably just need to define like what you actually want. All right, so multi-output raw root, okay, squared. Okay, so here we go. If true, returns MSE value. If false, returns RMS, and then a default is true. Maybe let's do both. Why not? Let's go ahead and do both. Just because. All right, so and I'm gonna go ahead and copy these down so I don't forget. All right, so mean absolute error, mean squared error. All right, I'm going to bring these on down. And okay, what are we doing? All right, so mean absolute error, so that's usually abbreviated as MAE. RMSE, root mean squared error, mean squared error. So this is basically the same thing except squared of the root mean squared error, and then R2 scores. Oh wait, I forgot. RMSE scores. I'm gonna call them scores, not errors. Nomenclature thing, not really a big deal. All right, so MSE scores. Oh, by the way, I am monitoring the chats of both YouTube and LinkedIn, so if you have any questions, feel free to drop them in the chat. And so far, no Russian bots in my YouTube. Usually I got at least 1 or 2 bots in here, but nothing quite yet. All right, so R2 scores, all right, equals, and then, so this is like a shorthand way to like instantiate little containers here. All right, so we need 4 of those containers. All right, so we're still gonna do a k-fold split because we wanna, make sure that we're not doing any sort of weird overfitting. I'm gonna, if I don't take this out, I'm gonna forget. Okay, so this is fine. Doing the split here is fine. Fitting the algorithm is fine. Getting the predictions is fine. All right, so then we need to actually change these. So before I delete them, these, I'm gonna say val MAE score equals, okay, maybe I will paste these so I don't forget. All right, so mean absolute error, and then we're going to do a yval, valpreds. Actually, I can go ahead and delete all these. No, we don't need those. Okay, so those, and then, okay, so that one's good. All right, so then we're going to do a val MSE error. Yeah, MSE. No, we'll do MSE first. MSE score equals mean squared error, and then so we're going to pass in the actual values, predicted values, and then we're going to leave that as is. Now we're basically going to do the same thing for RMSE, but recall that we have to adjust the parameter to actually get root. So val RMSE score, and what was that called? So squared equals true, false. Wait, sorry. If true returns, all right, if false return, okay, yeah, we want to do the false. So I already forgot what that's called. Squared. All right, so squared equals false. Squared equals false. And then finally, the R2 score. So val R2 score equals R2 score. And then just let me make sure that I'm doing this right. So let me just do scikit-learn R2 score. All right. So apologies for the little feet above me. Those are my daughters running around. We had a lot of fun in the snow today. So I usually work half days on Fridays, which is why I do these streams in the afternoon. So when I got off work at noon, we all went outside and played in the snow, and I built them a little tunnel. It was fun. Snow's kind of too powdery to build a snowman, so that was a little bit disappointing, but we still had a lot of fun. They're really sweet little girls. All right, yval. Oh, by the way, I did get a new picture of them with their preschool shots. Very prepare for instant cuteness, except my one daughter Elena on the left here is making like the goofiest face in the world. I don't know if y'all can see that. So those are my daughters. This one is Elena. She's the little one. She's about to turn 4 years old. And this is Emma, my big one, and she just turned 5 the day after Christmas. So she's a Christmas girl, and she loves Christmas. And I love her. Okay, back. Sorry, getting a little bit distracted here. All right, so valpreds, right? Valpreds. Okay, so all those are good. Then we need to do the appending of the scores. All right, so So we're going to do MAE scores dot append. Did I do that right? Yeah, let me MAE scores dot append val MAE score. All right, what do we got? RMSE. I don't know why I did that. This does not make any difference at all, but I just don't like the fact that I did that out of order, or at least out of the order that I define it. All right, so MSE scores dot append val MSE score, so mean squared error. All right, so RMSE root mean squared error scores dot append val RMSE score, and then finally R2 scores dot append val R2 score. Okay, I think that's good. All right, so these can be deleted, and then we need to get the averages correctly here. I forgot that we did this. So average MAE equals int, because and then we're getting the mean of the score, and well, do I want to do this? Do I want to do this as percentages? Maybe I don't want to do that this time. I did that last time. I still do want to get the averages though. That's right. Okay, so let me just go ahead and we can adjust this. This is easy enough to adjust later. So we're just going to do the mean here. All right. So, oh wait, what am I doing? I need to. I still need to write this whole thing. Okay. I just don't need the int. Sorry about that. All right. So mean of my MAE scores, average MSE equals mean of my MSE scores. Average RMSE equals mean of my average score of my RMSE scores, and then average R2 equals the mean of my R2 scores. R2 scores, okay. And then we can go ahead and delete all of this other stuff out here. Oops, no, don't want to delete the comment. Just the comment is still valid. And then finally, we want to do the printing out. All right, so print. So again, if you're curious, what is the F here? So this is called an F string. So the nice thing about an F string here is that we can type whatever we want as far as like plain language text. So average, mean, absolute error. And then we can put, within the brackets here, we can actually put our variables. So you can see that we define the average above, and then so we can do just that. So we'll go ahead and delete all these. All right, so, and then we're going to do that times 4 here. Average, mean, squared error. So this is going to be our average MSE. Boom, like so. Printing the root mean squared error. So F average root mean squared error, and that is going to be average RMSE. And then one more, finally printing the average R2 score is going to be our average R2. All right, there we go. Okay, and that should be our good to go function. So that was actually what took the most amount of time the last time, just because we had to work all this stuff out. But I think we should be able to churn through these a lot more quickly now. So I want to follow a similar format here. So that's what I'm coming up here. So algorithm number 1 is going to be a linear regression. I'm sorry. All right. I am just, and as you can kind of tell, I am a stickler for making sure that things look good, because if you know, honestly, like if things don't look good, or like no, if they don't look good, but if they don't have an intuitive flow to it, reading code can be very difficult, especially in the data science world. So please, if you're a data scientist, if you're a machine learning engineer, especially if you're working in Jupyter Notebooks, Markdown is your best friend. Leave Markdown cells as well as annotated comments. So, all right, so we have what, 3 cells, I think, and then, all right. So, all right, algorithm 1, 2, 3, algorithm number 2. Number 2 is the lasso regression. All right, All right, number 3, sorry. Algorithm number 3 is our support vector machine, more specifically our support vector regressor. Okay. Make a couple more cells here. And then number 4, algorithm number 4, support, no, wait, sorry, random forest regressor, and then another couple cells here. And you know, I'm just making things look nice and pretty for whenever we're ready to do the actual work here. Algorithm number 5. And this is this last algorithm I have actually not worked with at all myself, and that is the cat boost regressor. And I've actually never seen anybody use it, but the reason I'm using it is because I needed a 5th algorithm, and cat boost classifiers seem to work well. So you know, why not give the regressor a try? Okay, so now I'm gonna go ahead and run this all real quick. All right, so let's go ahead, and I'm trying to remember how we did this. All right, so I'm going to copy one of these cells down. Oops, didn't mean to do that. All right, so setting the hyperparameter grid for the linear regression, and then I'm going to go ahead and delete all this out. Linear reg params. All right, and I'm going to go ahead and do this for all these, and then we'll just try to make it easy on myself. All right, so for the cat boost regressor. All right, cat boost reg. Okay. So this one's random forest. Yeah, forest reg regressor params. I guess that's a little bit long. It's a little bit windy. All right, so we're going to call this just SVR for short, support vector regressor, SVR. Forgot to make support vector regressor. Okay, same thing here. Random forest regressor. Okay, all right, getting there. All right, so this one I can just change really quick. So lasso, like the TED. I don't know if anybody just got my reference there. Okay, all right, so we are setting ourselves up for success. All right, so there we go. Now we want to, then for the second cell in these, we want to instantiate each of the algorithms. So we're going to instantiate each of our algorithms. And I'm going to have to come back and do some of this. For now, we're just going to leave it like blank. All right, so cat boost. Reg, cat boot, no, not cat boost. So this is going to be random forest regressor algorithm. Algorithm, and then I'm going to copy and paste this here. I know this this part's a little bit tedious, so thank you for sticking with me here. But you know, the nice thing about this is when we get this all done, it's going to look nice and pretty, and then we don't have to come back and like do a bunch of like update. We're going to fly through this, I hope so. All right, so SVR params, I'm going to call this SVR algorithm. Okay, so that one's good. And then, so, all right, 2 more here. All right, so lasso regression. I'm going to delete this. I'm going to call this lasso reg. And then I'm just going to copy this here. And then, because this one's pretty close, we just have to change lasso to linear. Same thing here, linear. Okay, so, all right, two groups of cells down, 1 group of cells to go. And then, so we're gonna grab this here, except this is gonna be a little bit different. All right, so instead of binary classification, we call this function the generate regression model. So I've got to change this to generate regression model. Let's clean up our spacing. All right, then clean up the spacing some more. and then just one more time into our reusable regression function. Okay, so then we need to pull this down here, and then pull this down here. All right, now we're getting somewhere. All right, so then we pulled this here to here, then here to here. Okay, and then SVR. So SVR algorithm to here, SVR params to here. Okay, we're getting close. We're getting close, folks. Thank you for being patient. Generate regression model from here to here. All right, so lasso. I'm. You know, this is gonna sound stupid. Obviously, I'm gonna pick the model that performs the best, but I kind of hope the lasso one wins, just because I really do like the show Ted Lasso. Yeah. Okay, so one more. And so we can actually just change this really quick. Linear. Oops. And then linear. All right, so now all we got to do is start instantiating our things and start instantiating a parameter grid, and then we should be able to be on our way as far as actually fitting these things. Oh, and I have to import all these things. All right, so linear regression, scikit-learn, linear regression, scikit-learn, linear regression. All right, any questions so far? Y'all doing okay? Y'all have a good week? We got a lot of snow here in Illinois, as I was saying. So yeah, that was not fun in a way because we got snowed in and, you know, road's not great. But gotta have fun with my girls in the snow, which is definitely a win, huge win. All right, so from sklearn dot is it linear model? I guess it is linear model. Linear model import linear regression. Let's go ahead and do this for all these just really quick. And so I'm going to guess that the lasso regression is also in here. All right, lasso. That is not what I wanted. All right, this is it right here, right? Lasso. Yep, there we go. So it's just lasso. Okay. All right, so it's, well, no, I mean, I could, well, yeah, I am going to do it on the same line. I know I could have done this on the same, well, no, I'm not going to. Just to make it really clear. So this one, and then also the one up here that says linear model, I could have just all put on the same line. But just to make it really clear, we're going to separate these out. So model import lasso. All right, so what else do we got? The support vector class, the support vector regressor. All right, sklearn, scikit-learn support vector regression. Okay, SVR is from svm.svr. So again, same thing here. I could put it right here, but I'm not going to. All right, from sklearn linear, not linear model, svm, sorry. Import SVR. Okay, and then from, I'm gonna just wild guess, sklearn.ensemble import random forest regressor. Now let's see if I'm right. Who wants to make a bet with me? All right, scikit-learn support vector regression. Wait, no, we just did that one. My bad. Random forest regression. Okay, random forest regressor. Boom. That's what I'm talking about. All right. So then we can go ahead and actually instantiate these models down here as well. So I hate when it does this where it like keeps things highlighted. I know, I'm picky. This is the graphic designer in me coming out. All right, so what we just need to do is here, and I think this one was just called lasso, like the TED. So this one was just SVR, and then this one was the random forest regressor. And then just for fun, I am going to try just look to see what the cat boost regressor is. I'm pretty sure it's just called cat boost regressor. Cat boost regressor regression. All right, here we go. Yeah, here it is. Okay, so cat boost regressor. But what is this part of? You know what? Sometimes I just like to look at different examples. So there was actually one in here building a cat boost regression in 6 minutes. Oh, you know what? I never even thought to try an XG boost algorithm. Now I'm kind of tempted to try that out for both of these like both the regression and the binary. It's probably gonna have similar results. Well, I guess we'll see. Maybe. All right. So what did this person do? All right, just show me what you imported. All right, import. No, you're not importing it yet. Okay. So well, actually, maybe you did. Did you? And I'm just reading too fast. Cat boost is CB. And what? Oh, you just called it cv.pool, cv.regressor. Okay, so simple enough. So what I should be able to do here, and I'm going to comment it out again just because I'm having an issue with my pip installs right now, which is very odd. Okay, so this one's going to be cat boost regressor, and then that's not what I wanted. Come on, highlight. All right, and then stick this guy down here. And I'm gonna guess he's got this weird the weird verbosity thing here, so I'm gonna do silent equals true, just an assumption. Okay, so now what we can do is we can start to actually make some hyperparameter things here. Need scale equals true. Okay, so this is again where like, you know, I'm not a data scientist per se. I am a machine learning engineer, and the focus of my specific job, my day job, is that I implement models that were already created, meaning that I don't normally do like model creation itself, although, you know, obviously that's what we're doing here. You know, I'm not doing too bad, I don't think. But there are things in here that I'm not sure whether or not like they need scaled or whatever. So let's just Google that really quick. Linear regression. Does linear regression model need scaled data? And then, all right, so when to perform, because I've never found like one good, and I might write this if I actually do learn this well. I've not found a single good article, like an individual good article that will say that we need to do like standardization or normalization. So this person looks like they wrote one specifically for some things. All right, so linear. All right, summary. We need to perform feature scaling when we are dealing with gradient descent algorithms. Linear and legit. So this is interesting because I found an article that actually disagreed with this one. Like and we didn't actually do a logistic regression. So you know, not saying that this person is wrong. It's just I'm finding differing opinions. And then distance are very sensitive to the range of inputs. This is not okay. So this is not mandatory when dealing with tree-based algorithms. So you know what? I am just going to scale. I think I actually am going to go with the scaling on this one. Needs scaled equals true. And then also with the lasso, I don't think I'm going to do it. I'm definitely not going to do it for the random forest one, but I am going to do it for these first couple of needs. Scaled equals true. Okay, so how are we doing? All right, so let's go ahead and mean scale score. Oh, that is because df clean. Why is it doing this? All right, let me re-import my data here. All right, and then let's see. Did I spell something wrong? I am flying all over the place, as you can see. All right, mean scale score. Mean scale score is not found in the axis. Is it not called the mean scale score? Well, what is it called then? All right, let me check really quick. Maybe I misnamed something, or not misnamed, but I'm not thinking straight. Info. All right, so bean scale rating. Oh, wait, that means there's something wrong in here. Oop. No, wait, no, I did get it right here. All right, I was just being silly down here. I don't know why I didn't call that the rating. I should call it the score. All right, so the score is good to go. That's good to go. All right, now it's time to find some hyperparameters. So, and again, this is one of those things where hyperparameters or tuning is not like my forte at all. So I'm just gonna like Google to see what people did. Linear regression, hyperparameter tuning. Okay. Just tell me what you did. Show me what you did, because I'm gonna do the same thing. and you know, that's the thing with the at least with the grid search, finding the ideal hyperparameters is, I'm going to try robbing somebody's here and see how mine performs. And I'm just going to, if it appears like I could have different values that would perform better, which is actually what I did with the classification models too, is I can always adjust and rerun the thing. So grid search for classification, I don't want the grid search for class. All right, so hyperparameter random search, I don't want to do a random search, although that'd be interesting. I've never tried the random search, so that might be interesting. All right, so it looks like this person did all of these. All right, space equals dict. I don't know why I don't understand why people sometimes call their nomenclature what they did. Okay, so I'm just gonna paste this here, but I'm gonna follow this format here, and we'll see what happens here. So, oops, didn't mean to do that. Solver. Actually, you know what? Let's make it easier on ourselves. I know this isn't the correct syntax, but we can alter it very easily. All right, so solver. All right. Boom, comma. Don't forget the comma. And then let's do the alpha. Okay. All right, don't forget the comma. And like I said, if this doesn't work out, we can always try something else. Or alter our hyperparameters in such a way that it would perform a little bit better. Okay, so take these out. All right, true, false. Oops. And then lastly, do this. Okay, did I run this cell? I'm gonna rerun it just in case. All right, so if this all worked, linear regression is not defined. Did I not? Oh, that's because I forgot to rerun this first cell. You know what? This is one bad part about you working in a Jupyter notebook is that, if you accidentally skip over things, then that's a bad, or run the cells out of order, then that's bad. So let's just go ahead and rerun everything. Now, of course, we're gonna have to skip over the cat boost. All right, then let's run this. And then, all right, now this might take a minute because all those ones are running above. So let's take a quick breather, take a quick drink. Let's see how fast my Mac Mini can do all this stuff. Any questions so far? I know we're 45 minutes in. Ooh, accidentally hit my microphone there. Is my audio still working? Ooh, that did not sound good. Okay, how are things going up here? All right, so we're hanging on the binary classification model here, and that was to be expected. Because this one, I don't know why, this one takes a little bit longer to churn through all these things. Okay, so that is now good. All right, what did I do wrong? Invalid parameter alpha for estimator. Check the list of invalid parameter, alpha parameter. What alpha parameter? Oh, what is? All right, well, let me check here really quick to see what we can do. All right, scikit learn linear regression. All right, so, okay, well, apparently this person's, did I just grab like a bad set of stuff because none of these are in here? Parameters fit intercept equals true, normalize, copy, and jobs. Okay, so it looks like this will only speed up in the case of sufficiently large problems. Positive. So maybe you can't really set any. Okay, so maybe, I'm going to go ahead and leave this as an empty set, although I wonder if this is even going to work. RMSE scores is not defined. It isn't. I forgot to put the S there. Yeah, that wouldn't work. Okay, so there we go. So here's our mean absolute error, root mean, or mean squared error. Obviously, we didn't have any best hyperparameters because we didn't have anything, and the root mean squared error is this number. And so the mean squared error, the root mean squared error, I don't really know how to interpret these numbers. You know what? Here's the interesting thing though that I just found out is that apparently if I run all these things, then they're gonna run even if I don't put anything in them. Oh, obviously that last one wasn't gonna work. Okay, so if I don't put anything in these, why did this one? Is it because I scaled the data? Like, I don't know why the linear regressions are so different. That's odd, is it not? Did I do something wrong? Um, okay, so apparently I'm going to need to teach myself a little bit more about support vector regression to understand like uh, some of these scores that we're seeing. Well, let's go ahead and do it. I have the time now. Why not? All right, so interpreting. All right, so mean absolute error. Because I thought I understood these, but maybe I don't. Because I thought the mean absolute error was just like how far away, like an individual, like in general, like how far away are your scores from like what your expectation is. And so that's where I'm kind of thrown off. Is like, all right, so linear, these are fine. I would expect. So what this is kind of saying here is I would expect like the mean absolute error. We're basically saying, okay, so if I guessed that the score of the movie is 6.8, then the mean absolute error is going to be 1.6 up and 1.6 down from 6.8. So what would that be? So 6.8 plus 1.1 is 7.9. And so that makes sense. What I'm thrown off by is when we see the linear regression here and we have a mean absolute error of just like a million. Like, why the heck is that the case? And out of curiosity, let's go ahead and take this out and see what happens. All right. Okay, so maybe linear regression doesn't need scale because these numbers look a lot more accurate. And even without doing any sort of hyperparameter tuning, let's just go ahead and look at the scores as is. So basically, you want at least for these other, maybe my intuition is right. Now, the only one I don't have an intuition on is R2 score. I'm not really sure what R2 score is, but my intuition on these three, and these are calculated a little bit differently. And so actually, I would actually pay more attention. I'm more concerned with the mean absolute error in root mean squared error as opposed to the mean squared error. In fact, I don't even know why I included the mean squared error now. You know what? And actually, let's go ahead and take that out because I don't really like the mean squared error because it kind of gives a weird thing, weird vibe. So let's go ahead and take the mean squared errors out, and this should be. And that's the nice thing about using a function like this is we can then take all these out very easily. Boom, 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 boom. Okay, so I took all those out. All right, so let's look at what is an R2 score, because R2 score is the one I'm not really super up to speed on R2 score, but I am familiar with the other twos. All right, so R2 score is boom, boom, boom. All right, coefficient of determination. All right, why are these terms important? Bias, overfitting. What is an R2 score? So R2 score varies between 0 and 100%. It is closely related to MSE, but not the same. The proportion of the variance and the dependent variable is predictable from the area. Okay, so another definition is total variance divided by total variance. Okay, so what if you have a negative R2 score? What is this article is not too great with explaining things to me. All right, what is a good R2 score? So apparently in finance, above would be showing a high level of correlation. Is this the correlation thing? All right, so best possible score is 1.0, and it can be negative because the model can be arbitrarily worse. A constant model that is predicts the value constantly for blah 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 would that always predicts the expected value of y disregarding the input features would get it. Okay, so just tell me, what should we expect here with these? All right, so we have an R2 score of 1 here. And so when we are all right, so the true values here, so we got above and below, -3, and we have a couple that are above here. Let's just look at the Wikipedia article. Let's try to understand this a little bit better. Okay, and I'm gonna, honestly, I learn better by watching videos, and I'm sure there's a good video about this on, oh my gosh, why is the name Khan Academy? I'm sure Khan Academy has a good video on this. All right, the dependent variable. Okay, so in both cases the coefficient. All right, so what if you have a negative determinant? All right, negative R2 score. All right, so negative R2 score. When is R2 score negative? Bottom line, R2 score cannot be negative as it is the square. Okay, well, that's not true because we have negative scores, unless this is not a true R. Well, actually, let me look. Maybe there is like some sort of variable that I didn't set. So R2 score, sklearn. Maybe there is. Maybe it's just giving me the score that is not squared. All right, so R2 score. coefficient, or maybe I'm misunderstanding something here. All right, best possible scores. All right, I'm gonna stop talking because it's hard for me to read and talk at the same time. All right, I'm like, maybe negative. All right, the metric is not. All right, that's fine. So we have a negative score, so the true values are kind of far off. All right, so this one. All right, this one's pretty close. What? Non-negative least squares. Okay. For dummies. Well, I am a dummy when it comes to some of these things. I'm not a math major. Actually, I'm not a computer science major. I'm a business administration and leadership major. Who happen to learn how to do these things along the way. And you're learning with me right now. So some of you who, if any of you are screaming at your computer right now, I apologize. All right. So this is the one term amongst all that novice and budding analysts when it's quite popular. Okay, so this term, all right. Below is the result of Google Trends among adjusted R-square, however. All right. Well, you showing me examples is not really helpful. All right. Is a statistical measure to understand how close the data is fitted to the regression line between 0 and 100. What if it's negative? Indicates that none of the variability of the response data is around the mean. All of the variability is around its mean. Not exactly. There are two reasons. All right. But what if it's not squared? Get out of here, thing. All right. Total sum squares, residual sum squares. Well, so what is going on with scikit-learn that we're getting a scikit-learn R2 score? Because it can be negative because the more a constant model that constantly always predicts the expected value of y disregards the input data, and we'll get a R2 score of 0. Okay, well, out of curiosity, let's try something out. I just want to see like what happens if we just do a print of the first couple scores. Do I want to do that? Yeah, let's try that out. All right, so printing the actuals versus predictions. Print f actuals, and then so we want to get the y-val. I think it's just the 3 like that. I think that's right. I'm not very okay. So that's val. Predicted is val preds. Okay, let's see how this fares. Uh-oh. Forgot to put. That's the one bad thing about the f string. You tend to forget to put that last little quote in there. Okay, so actuals, predicteds. Okay, those were okay. So that one was kind of, the first one was way off. Next two not terrible. Well, that one's kind of bad. All right, so this one here. So we got a 7 out of 10. So that one's pretty spot on. That one's pretty bad. This one's pretty bad. Oh my gosh. This is not good. All right, and then finally we have the actuals here of all right, so 0. Is this right? So 9 out of 10, 8 out of 10, 6 out of 10. Okay. Oh my gosh, these are so bad. And granted, remember, we're working with a really small data set, so I'm not gonna beat myself too terribly much over it. This is just like a fun little project, and so this one's. I mean, yeah. So this is actually looking quite right. Like the mean absolute error is probably that much off. Okay, so okay, all right. Right. Okay, all right. Okay. Can I say all right and okay like 10 more times? You know what? if you're not having fun, then why are we here? That's the whole reason I'm doing the stream. Is, you know, this is my idea of fun. Because I have a weird idea of what fun is. All right, so let's try this again. Let's just look for linear regression hyperparameters. Well, now I'm curious, because we're using grid search, which kind of you have to define your own. Now I'm curious, like, how the random search works, and I might try to figure that out on the side. Like, yeah, I'm curious here. What's going on here? Okay. Sorry. And by the way, I love Medium. Granted, I'm a little bit biased since I'm a frequent author on Medium myself, and I do get a little bit of money from that. Okay, regularization, range grid. Okay, all right. So you talked about hyperparameter tuning, and then I never actually did any hyperparameter tuning. You're just talking about crap. Okay, so this article is not very helpful, unfortunately. All right, is it possible to tune? Is it possible to tune these things? There's always room for improvement. Blah blah blah. Set params. Research would be blah blah blah. This is a very open question. You should just look at. Okay, well, all right. Linear regression, tuning. All right. So fit intercept. What calculate whether to calculate the intercept of the model is up to intercept will be calculated in calculations. The data expect to be center normalization. Default is all right. So copy x. If x is copied, then it may be overwritten, then it's fine. No, that's fine. I'm sorry. Number of jobs. I don't see anything in linear regression that like we can necessarily tune. Forces the coefficients to be positive. This option is, yeah. So I don't think we like linear regression here. Like there really is any hyperparameters we can tune. So maybe that's why I'm not finding anything. Okay. How about Lasso? All right. Ted, where are you at? All right. So Lasso. It looks like we can do some stuff for Lasso. So it looks like Lasso, we got an alpha value. Maybe that's it. A tolerance value. Okay, so how about Lasso regression hyperparameter tuning. All right. And maybe we should try a different algorithm aside from just these ones that we tried. Actually, let me go back and look because I'm curious what the scores are. So, and I should truncate these scores to where like I don't have so many decimals. But for now, this is fine. So, 1. All right. So far, Lasso's perform a little bit better. Support vector regressions perform a little bit better than all those, and then random forest regressors, but more or less the same. Yeah. Actually, so it looks like number 3 or number 4 might be performing the best. Okay, so let's come back here. Cannot be hyperparameters to tune. I'm just putting a comment in here. All right, so the Lasso regression hyperparameters, Lasso ridge, number of samples, libraries we use, general tips. Do not copy. Once again, the example is without scaling, and there. Okay, well we are going to do scaling here on this one. All right, so doing a fit. All right, okay. Where did this person? All right, so they're Lasso alphas. Okay, so they just did the alphas. It looks like alphas, and then they did this. Apparently, I can't copy that. What do I want to do here? 0.2, 21. Alpha equals b dot min space 0.2, -1. And in case you're curious what linspace does, is saying, okay, I want, oh man, I thought I understood this, but maybe not. I thought it was, I start at 0, I end at 0.2, and then I take a step at 21, but that doesn't make any sense. Okay, 0, 0.2, 0.2, 21. Yeah, what did I do wrong here? Not equals, colon, 0.2. Okay, that's fine. All right. Did I do that right? 0.2, -1. Well, let me check real quick. NumPy linspace. Well, actually, why did I even do that? I could just look at these things here. So lasso reg params equals, okay, so that's all right. So 0, 0.1. I don't know what this 21 value here is doing, because like, here, let's try this out. Okay, never mind. I wonder what the default value is. Okay, what is the default value? All right, linspace, start, stop. No. Oh, okay, so it actually does have a default value of 50. Interesting. So what it's basically doing is here, okay, linspace, you have returns evenly spaced numbers over a specified interval. So I was right. So you have a start and a stop, and then then you have a number of steps. So this person did 21 steps between these two, which produced, what was that again? Let's go ahead and look. Lasso reg params. So that produced all of these. Let's go ahead and make it an even 25, because why not? And we still got a constant alpha here. Well, so this is interesting. So this is where, you know, I said like we need to maybe analyze, because this is pulling the alpha from the very top here. So let's try something different out here. So let's do make 0.2 our starting, and then maybe make just around 2 as our top. And then let's see how that fares better. Okay, so that's a little more better. Okay, and I can delete this. All right, and then are we faring much better? We're faring better here, it looks like, than just like a straight linear regression. So far, Ted, you're doing great. Any questions so far? No Russian bots today. What's going on? I'm disappointed. All right, so hyperparameters of the all right, support vector regression hyperparameter tuning. Okay, so using grid search. All right, so tell me what you did, Miss. This article, where are you? All right, so using grid search CV. That's what I need right there. If this little thingy go away. All right, little thingy is a technical term. I'm an idiot. Okay, so I just want to grab these things here. So C. All right, and then I don't know why they're specifying the kernel. In fact, I'm not going to specify the kernel at all, because there's only one. All right, so I can go ahead and take these out, SVR params, and then all right. So far, this is pretty close to the lasso. All right, yeah, this is pretty close. And then again, I have to really, I'll need to study a little bit more offline of the actual like differences here, like what the R2 score means here, because the R2 score is pretty different here. Okay, and then finally, let's go ahead and just do the random forest classifier. So, or I'm sorry, not classifier. I'm just curious, is there a random forest? Random forest. Okay. Random forest regression hyperparameter tuning with Python. Okay. So this, wait, no. This is I think this is a classifier. Oh no, this is a regressor. Okay. Never mind. All right, let's look at this person's hyperparameter grid. Oh, okay. So apparently I can specify the same hyperparameters. So I'm going to do that. I'm just going to do that from above here, see how that fares out for me. All right. So let's go ahead and copy all these. All right. So random forest regressor, regression hyperparameters. All right. This one's going to take a little bit longer, I know. Take a quick sip. And we're doing pretty good on time. You know, unfortunately, we didn't get the regressor. But, you know, while this is still running, I think in the next stream, I'm going to pick the 2 candidate models here that perform the best, and I'm going to create a full inference pipeline. And so specifically what I mean by that is we're going to take the hyperparameters that were best from whatever our candidate algorithm here is, and we are also going to pair it with our actual feature engineering. That way, whenever we create like an inference pipeline later to actually predict new movies, then we can just pull like take the input data, shove it through one serialized model, one pickle file that does all the feature engineering, all of the like the model inferencing, and then like spits out a score on the other side. And so that's what we'll probably do in the next live stream here. Okay, so it looks like this one with the hyperparameters fared maybe the best. All right, but something interesting to note. I'm gonna do some more hyperparameter alteration here. Alteration is not a word. All right, so max depth. Where's max depth? Is 20. So I'm gonna increase this one. So maybe make 25, maybe 30, and 50. Min sample split. That one's pretty even, but I'm gonna just, maybe we'll tighten it up. Let's see how 11, 12, and then maybe a 9 fares. All right, not 8. I meant to say 9, and then min samples leaf is a 10. Oh, no, I'm sorry, is a 1. Let's keep these. Let's see how these fare. Oops. Didn't mean to do that. Although I think that would still technically work. And I still got to figure out what's going on with my CAD boost here. Now I do know, because I'm doing also my work on my Microsoft Surface over here, is like worst case scenario, I can complete all the work over there. And then let's see how this goes. Oh, no Russian bot today, but now I've got some suggestive people in my YouTube stream putting suggestive emojis, suggestive bots. So I kind of miss the Russian bots now because I don't really want adult themed things in there. All right, so we're across all of these, we're getting about the same root mean squared error. Now here's the really disappointing thing is, on a scale of 1 to 10, like an error of close to 2, it's pretty awful. Like that's not great. So what I might do is ranges. I might do ranges of these things. Yeah, these guys are not going to be happy. But that's the problem with working with really small data like this. Now that this is done, we can see so max depth 20 is still about right. 3 min sample split is 10, and then number of estimators is 50. All right, well let's try increasing it in. All right, 50 from 50 to 75 and 100. Max depth 20. Let's go ahead and take out the top value and then put a 15 in here. See how this fares. This is non-scientific, obviously. Like, if I was smart, I would be and this was what. So I do want to do a future live stream on a open source tool called MLflow, because MLflow will track all of your experiments for you. So then we can go back and see how I alter these parameters very easily to see like how these things fared amongst each different experiment. Because obviously I'm not writing this stuff down, so I don't remember like what these things are. But that's the nice thing about MLflow. I really like MLflow. Okay, so min sample split 10. Okay, so that's about right. And then min samples leaf 3. Okay, well, all right, let's one more time. Let's see how this fares. But so far, even though we're seeing a little bit of difference or like a little bit of betterness with some of these models, like you could see, like in generally speaking, they're all performing about the same. Like, and that's kind of to be expected, especially with like small data like this. Like, so when I mean small data, I mean we're working with 125 records. Usually, you want to work with thousands, more like tens of thousands, hundreds of thousands, millions of records. So 125, not much, not great. But what are you gonna do? I can't force the reviewer to review a lot more movies for me. Okay, so this is gonna be our last one, and then we'll go ahead and wrap up for the day. Okay, so sorry, I'm just trying to mouse over here, but this is not letting me mouse over this thing. Is it done yet? Nope, not done yet. I want to see who that is. Okay, so yeah, we're getting about the same scores each time for all these algorithms. And of course, I don't know what the cat boost one is because I can't load it. But basically, this is it. So I'm going to go ahead and save this, push this up to Git, and call it a day here. So as far as model candidates go, you know, I'm so confused. All right, as far as model candidates go, we're going to call it a day here. I think we have a couple of different, you know, basically what we found here is that, you know, the ensemble models really aren't performing that much better than like a simple regression model. So I think for the classification model, I am probably going to go with a random forest classifier. And then for the regression model, I need to understand the R2 score better. It seems to indicate that, like, if you have a higher R2 score, that it is better. Don't quote me on that, of course. And if that's the case, then the support vector regressor seems to be winning out each time. And so we may stick with that one. Oh wait, I take it back. The Lasso Regression actually seems to be, except the mean squared error is, actually RMSE is a little bit better here. I kind of want to go with Lasso just because, you know, like I said, this doesn't matter because it's a kind of a silly project. I kind of want to go with Lasso because Ted Lasso. And that is a don't, if you work for a big business and you tell your boss that, like, don't, because that's a really bad idea. I picked the Lasso regression algorithm because of Ted Lasso. Like, that's a really stupid, like, lead with numbers. But you know, even these numbers though, like, we're seeing, like, you know, things are pretty similar throughout here. And okay, so I saved. Let me go ahead and push this up by term. All right, repos, cd movie ratings model, git status, git add all. Oops. Yes, with 2 dashes. Sorry. Git commit. Adding regression candidates to model selection notebook. Git push origin main. Okay. And then if we go into Git, did that push right? Yep, that did push right. And then, so if you want to do, oops, sorry, wrong thing. If you want to follow along with my project here, so my personal account here, github.com. Oh, this is interesting. Who started this? Sorry, oops, I didn't mean to do that. I just want to see who started it. Dang it! How do I check to see who started? Sorry, this is a side project I'm thinking about working on. You didn't see that, even though it is public. All right, so moving ratings model. Okay. All right, so this is my effort. So notebook is here, model selection is here, and then you can see everything we did today, including with all the scores and stuff. And then you can all see my error down there. So I will clean this up later. Let's go ahead and call it a stream there. So hope you all had found this to be interesting or enjoyable or both or informative, all of the above. But for now, let us go ahead and wrap up the stream. I'm having girls' night with Dad. And so we are going to, they really want to watch The Polar Express. I know that's a Christmas movie, but my girls love Christmas and I love them, and therefore they win. And they're sweet. So we're going to eat popcorn. We're going to watch that movie. And then tomorrow's my mom's birthday, so we're going to go down to Decatur and wish her a happy birthday. But otherwise, I think I'm going to have an easy weekend. Hope you all have a great weekend. Thank you for watching, and we'll see you in the next stream.